We will consider strength of materials approach to calculate material properties of a unidirectional laminate. And the figure shows a general composite body with x1, x2, x3 axis. It's a unidirectional lamina, and you can see the fibers here within the composite. In the applications of micromechanics, we work with a representative volume element. This is the representative volume element. Contains a single fiber embedded in the matrix material. Its thickness is TC, height is H, and as a general length LC. And this in green cross-section is the fiber cross-section. This is the representative volume element. Therefore, the representative volume element is the smallest part of this composite body that is capable of representing the behavior as a whole. And in micromechanics applications, we work with a representative volume element. However, we are going to further simplify this representative volume element, RVE. And we will approximate the fiber as a rectangular block here, a rectangular body with a rectangular cross-section, or a fiber with a rectangular cross-section. And that is our simplification. This is the fiber now. And that is the simplified RVE. Fiber thickness is therefore TF. Each matrix thickness in this representative volume element is TM over 2. And for this reason, total thickness TC is TM plus TF. We can define the areas here, cross-sectional area of the fiber, for example, AF. And this is TF times H, because the height is H. And cross-sectional area of the matrix, total cross-sectional area of the matrix in this representative volume element, that's TM times H. Now, this is an inhomogeneous material. In our derivations, we will also need a homogenized RVE. Homogenized representative volume element, and I can show it here. Suppose that this is just a simple plate. It's homogenized, or it's a representative volume element, X1, X2, X3. Its thickness is TC, and height is H. Now, the properties are known. The modulus of elasticity in X1 direction is E1. In X2 direction, it's E2. In this direction, it's E2. It's a homogenized RV. This is the actual RV, which contains the fiber and matrix, and they have different properties. Fiber cross-sectional area, AF, is TFH. Matrix cross-sectional area is TM times H. And composite cross-sectional area is therefore TCH. Cross-sectional area, TC times H. And I can define volume fractions for the fiber and the matrix. volume fraction of the fiber, for example, is V fiber over V composite. And volume of fiber is area fiber times length. Let's say that this is the length of the RVELC divided by A composite times LC. For VF is the AF over AT. Volume fraction of fiber is A fiber over A composite. You can define A composite also in this figure. And this is at the same time equals TF over TC, because AF is TFH, AC is TCH. Fiber volume fraction can be written in this form, and therefore matrix volume fraction is A matrix over composite, and this is T matrix over T composite. These definitions are going to be used in our derivations. Now, we can work with this representative volume element. We'll first use it to find an expression for longitudinal Young's modulus. Or elastic modulus. As I mentioned, we will consider this, and let me copy this, present to the volume element. We have to apply it in the derivation of longitudinal Young's modulus. What is longitudinal Young's modulus for this homogenized element? Which one is longitudinal Young's modulus? Which one is the longitudinal Young's modulus here?
Isn't it E1, John?
Yes, it's E1. So we will derive an expression for E1. And I'm going to erase some of these designations. This is known. Apply a force on the representative resultant force on the representative volume element in the longitudinal direction in x1 direction. And suppose that this resultant force is FC, sub C. As a resultant force, it causes elongation of both, causes an elongation in both the fiber and the matrix. And when you apply such a resultant force, the total force FC is shared between the fiber, is F sub F, and the matrix, F sub M. And the sum has to be equal to FC. Fiber force plus matrix force is equal to total force acting on the composite as a whole. And we can write down fiber force, which is sigma in the fiber stress times A fiber, and matrix force is sigma matrix times A matrix. These are no different stresses in the fiber and the matrix in this inhomogeneous representative volume element. Furthermore, we could express stress in the fiber. This is E fiber modulus times epsilon fiber, that's its fiber strain. And sigma matrix should be equal to E matrix times epsilon matrix. These are for the fiber and the matrix. And if you think about this homogenized element here, suppose that this is the homogenized RVE. Let me erase some of these designations. If composite is also acting, this is the equivalent element. We are applying the same force here, F composite. And therefore, you can write F composite as sigma composite in this homogenized RVE times A composite. And how do we express sigma composite? What is it equal to? Which elastic modulus for sigma composite?
Isn't it E1 hocam?
E1, yes. E1 times epsilon composite. There's separate stresses in the fiber, matrix, and in the equivalent element are written. If you all substitute into this force balance, F composite equals F fiber plus F matrix, so we get substituting and how can I simplify this result? How do we simplify this? You can think about the deformations.
Are strains going to be equal to each other?
Yes. That is the final expression, E1 composite, E1 epsilon composite AC equals EF epsilon fiber AF plus EM epsilon M AM. And as when you apply this resultant force, the strains in the fiber and the matrix should be compatible. They are equal to each other, and that strain has to be equal to the strain in the equivalent homogenized element. In other words, epsilon composite equals epsilon F, and this is equal to epsilon M. And these are canceled out. E1 AC equals EF AF plus EM AM. How can I further simplify this result? We will divide by AC, and AF over AC is VF, AM over AC is VM. That leads to E1 equals EF VF plus VM. And that is E1, an expression for E1, EF, VF plus EM, VM, modulus of elasticity on the composite E1 is EF, VF plus EM, VM. This is referred to as rule of mixtures. EF should be fiber modulus in longitudinal direction. Longitudinal direction. Certain fibers are not isotropic. They have different moduli in longitudinal and transverse directions. Whenever you apply this equation for E1, you have to consider the fiber modulus in the longitudinal direction. But some fibers are glass, they are isotropic. So that doesn't matter for the glass fiber. And EM is matrix modulus. Matrix material is isotropic. If the volume fraction is also given, you can find E1. Any questions about this? One final remark. How can we find the properties for fiber and the matrix? For representative materials, you should refer to table 3.1 and 3.2. Fiber and matrix properties are given in these tables. And you can find properties of different types of fibers, graphite, and I can show you actually this table. This table 3.1, it includes fiber properties and the materials provided or considered here are the fibers considered are graphite, glass, and aramid. For glass, for example, axial modulus is equal to transverse modulus, but that's not the case for graphite fiber, and the aramid fiber. Whenever you are computing E1, you need to use the correct value, which is the axial modulus for the fiber. Table 3.2 lists matrix properties. 3 different matrices are given, 2 polymeric materials, epoxy and polyamide. Aluminum properties are also provided. These are all isotropic materials, therefore. In the computations, for example, for an epoxy composite, modulus of elasticity is 3.4 gigapascals. Any questions about these results or the table? Okay, then we will continue in the next lecture.